Hello dear students, we are back again with another video lesson. I hope you are all doing well. In a previous lesson, if you remember, we studied the electromagnetic induction and the how can you induce the current in a circular loop by changing the magnetic flux, and also we studied the Lenz's law. According to Lenz's law, the induced magnetic field that created by the induced current in a circuit, in a solenoid, it opposes to the change of the magnetic field that created by it, okay? And today, inshallah, we are continuing to explain the Lenz's law and the questions that related with the Lenz's law and the Faraday's law. We stopped in question 2 in a previous lesson. Question 2 in chapter review says, explain how Lenz's law allows you to determine the direction of induced current. The answer is the direction of the induced current. The direction of what? Of the induced current is such that it is magnetic field. The magnetic field of what? Of the induced current. Like, for example, the bar magnet, the magnetic field of a bar magnet, it goes to induce current in the circuit by moving the magnet or coil into the magnetic field, induces the current, okay? So this is the induced current. And this induced current in the solenoid induces the magnetic field, okay? So this induced current induces what? Induces the magnetic field. Now, how many fields do we have? We have 2 magnetic fields, okay? These 2 magnetic fields, according to Lenz's law, they opposes each other, okay? The induced magnetic field is opposes to the change of the magnetic field of a bar magnet. So who stated this? The Lenz. Lenz was the first scientist who stated this. Question 6, guys. Explain how Lenz's law illustrates the principle of the energy conservation by opposing change in the external magnetic field. Opposing change in what? Opposing change of the bar magnet, external magnetic field. Because the induced magnetic field opposes change of external magnetic field. External magnetic field. By opposing change in the external magnetic field, the induced magnetic field prevents the system's energy from increasing or decreasing. If you remember, in a previous lesson, we studied that the total field is constant, okay? When the magnetic field of a bar magnet increases through the coil, so the induced magnetic field, it will be opposites, and the force between them becomes repulsion, and the total magnetic field stay constant, and the induced magnetic field keep the total magnetic field constant and unchanged. So we have some tips and some notes about the Lenz's law. The direction of the field of induced current does not opposes the applied field. The direction of the induced current or the direction of the induced magnetic field does not opposite to the applied field, which means external field, but rather the changes in the induced fields. And the induced magnetic field tends to keep the total field strength is constant, okay? So the induced magnetic field does not opposite to the external and the applied field. Rather, it opposes the change of the applied magnetic field. When the magnetic field increases, the induced magnetic field becomes repulsion. The force between them becomes repulsion, and they resist this increasing. When the magnetic field decreases, the induced magnetic field will be opposite of this decreasing, to stay and to keep the total magnetic field unchanged and constant. Lenz's law does not provide information about the magnitude of the induced current. Lenz's law, he didn't provide the information to determine the magnitude of the induced current. To determine the magnitude of the induced current, you have to use the Faraday's law. We will study, inshallah, in the next pages. Lenz does not provide information about the magnitude of induced current or the induced EMF, but Lenz's law allows you to determine what? The direction of the induced current. Lenz was the first scientist who discovered and determined the direction of the induced current in the coil. To calculate the magnitude of the induced EMF and current, you must use Faraday's law of the magnetic induction. Guys, look at this question. This is without a question, be careful. In the figure below and the figure shown beside, what is the direction of the current in the resistance? Okay, we have a coil of wire. and we have a bar magnet. North and south. Branch A, if the magnet is moved to the left, the magnet moved to the left, okay? So it means that the north pole moves away. So what will be the direction of the induced current in the resistor? In this resistor, what will be the direction of the current? So usually we have to find the direction of the current in the resistor only. But when the north pole of a bar magnet moves away from the coil, the end becomes opposite pole. If you move away north pole, this end becomes what? This end becomes south pole. Opposes each other according to Lenz's law. This end becomes what? This end becomes south. In the case of moves away, the end of the coil becomes the opposite pole that we move it away. We moved away north pole and this end becomes what? South. If this end is south, this end should be north. According right hand rule, to determine the direction of the current, we have to use the right hand rule. Put your fingers in the direction of the north, okay? This is for the direction of the north, and the 4 fingers represent for the direction of the current. North here, the direction of the current is down, okay? The direction of the current is down. So in the resistor, the direction of the current is directed to where? To the right. To where? To the right. In the case when one moves away the north pole from the coil, the end of the coil becomes south and this end becomes north. According to right hand rule, you can determine the direction of the current. In this case, the direction of the current is directed to the right, as you can see here. From left to right, it means that directed to the right. In the second case, branch B, guys, look. Sorry. And branch B, we have like the same coil. And we have a bar magnet, north-south. In branch B, if the magnet is moved to the right, moves to the right, the north pole approaching to the coil, this is approaching north. If you approach north pole, this end becomes the same pole, opposed to each other, according to Lenz's law. If this end is north, this end becomes south. Put your fingers, the thumb is in the direction of the north and the 4 fingers is upward. Okay, here the 4 fingers is where? Is upward. Upward, upward. So the direction of the current is directed to where? To the left. If you oppose the north pole into this coil, the direction of the induced current in the resistor is directed to the left, from right to left. In this way, you can answer the questions. Question 5, guys, be careful. This is very good question. Listen carefully with the full focus, please. Rapidly inserting the north pole of a bar magnet. Rapidly inserting what? North pole of a bar magnet. So you have to draw a bar magnet. This is bar magnet. North and south. Rapidly inserting the north pole of a bar magnet into a coil of wire. This is bar magnet. And we have a coil of wire. And connected with the galvanometer. Connected to a galvanometer. And the galvanometer, when we're inserting the north pole into the coil, the north pole of a bar magnet approaching north pole, okay, as the question mentioned, inserting the north pole of a bar magnet. So we have to approach the north pole into this coil and the solenoid, okay? And in the case of approaching the north pole, this end becomes the same pole, north, and this one becomes south. When we insert the north pole into the coil, the galvanometer, the needle of the galvanometer deflect to the right, okay? The needle of the galvanometer deflected toward to the right. Guys, look. So when we insert the north pole of a bar magnet, the needle of the galvanometer deflected to the right. So the direction of the current is the same direction of the deflection of the needle. Be careful, guys. For example, if the needle of the galvanometer directed to the right, what do you mean by this? It means that the direction of the current is also directed to the right. Why? Because the direction of the current has the same direction of the deflection of the needle. The deflection of the needle has the same direction of what? Of the current. For example, if the deflection is, if the needle deflected to the right, the current in the galvanometer also directed to the right. If the needle directed to the left, the current in the galvanometer also moving from right to the left. In this case, because the needle directed to the right, the direction of the current also directed to the right. Okay. What will happen to the needle if you do the following? We have three questions here. We have three branches. Branch A, pull the magnet out of the coil. So we have to put out this magnet into the coil. First of all, you have to draw the figure because the figure is not given in this question. By approaching the north pole, this end becomes north and this one becomes south, and the direction of the current directed to the right. How did you know that this is directed to the right? By the galvanometer, by the needle of the galvanometer. And without the mention of the needle of the galvanometer, also you have to know the direction of the current in this circuit directed to the right. How? By using right hand rule. Put your thumb in the direction of the north and your fingers down. Okay, here is down. The direction of current is down by inserting the north pole. Okay, is the same thing? Yes. Current to the right. Branch A, pull the magnet out of the coil. So you have to draw the bar magnet, north, south, okay? And a coil of wire. In question A, pull the magnet out of the coil. Out of the coil, it means that move away. Out of the coil. If you out the north pole of this coil, of the bar magnet of this coil, this end becomes opposite pole in the case of moves away. If you move away the north pole, this end becomes what? South, and this end north. Okay. Now we have the direction of the magnetic field. If you know the direction of the magnetic field, you can determine the direction of the current very easily by using right hand rule. Put your thumb in the direction of the north, and current here is upward. Sorry, we don't have resistance. We have a galvanometer here. Okay. And instead of resistor, we have what? We have galvanometer. So the current is directed to the left. When the current directed to the left, the needle of the galvanometer also must be deflected to the left, because the deflection of the needle has the same direction of the current. So the answer of this question, the needle deflects to the left. By pull out the north pole of the bar magnet from the coil, the direction of the needle directed to the left. Why? Because the direction of the induced current in the galvanometer directed to the left. B, let the magnet sit at rest in the coil. If you let the magnet sit at rest in the coil, it means that there is no movement, there is no approaching, there is no moving away. Both the magnetic field and the coil stay at rest. There is no relative motion. Without relative motion, without change the strength of the magnetic field, without change the area of the coil, there will be no electromotive force. There will be no induced current. So that is why the needle does not deflect. Answer for branch B, no deflection of the needle. No deflection. Why? Because both the circuit and the magnet are at rest. There is no relative motion, and there is no change in magnetic field, and there is no change in the area. Branch C, throws the south end of the magnet into the coil. So we have to approach the south pole of the bar magnet. Approach south pole. Guys, look. Approach south pole. Approach south pole, thrust or approach the south pole into the coil. The end has the same pole according to Lenz's law. In the case of approaching any pole, the end of the coil that approaches the magnetic field, the bar magnet and the external magnetic field becomes the same pole. By using right hand rule, the amount of the direction of the current here is upward. Okay, so the current is directed to the left. So that is why the deflection of the needle also directed to the left. Needle deflected to the left. Okay, so we answered all branches of the question 5 in chapter review. One of the very nice and very challenging question in this section. Let's solve question 7, guys. Question 7 in chapter review. The question says, does dropping a strong magnet down a long copper tube induces a current? Absolutely yes. Why? Because by dropping a bar magnet into the tube of the copper and conductor, this bar magnet, in the case of like moving downward, there is a relative motion between the bar magnet and the tube, the copper tube. So that is why the current induces in the tube, and this current induces a magnetic field that opposes the external magnetic field. So that is why the motion of the magnet will be slowed down. Okay, so the induced magnetic field has effective of the motion of the dropping object into the copper tube. Thus, dropping a strong magnet, for example, if we have a tube, assume that we have a tube. Dropping a strong magnet. Guys, look. Dropping a strong magnet. Dropping the strong magnet into the copper tube, does this magnetic field induces the current in the tube? Absolutely yes, of course. Why? Because there is a relative motion approaching North Pole into the coil. Okay, so the end of this coil becomes North Pole, and we have two fields. They are opposites to each other. And so the answer of the first part, the question says, does dropping a strong magnet down a long copper tube induces current? The answer is yes. If so, what effect will the induced current have on the motion of the magnet? The induced current has effective of the motion of the magnet, and it goes to slow down. Why? Because dropping the bar magnet, approaching the magnet into the coil. In the coil, the magnetic field, the induced magnetic field opposes the external magnetic field. So that is why the force becomes repulsion force. And this repulsion force, it goes to slow down the movement and the motion of the bar magnet. So the resulting force, which is repulsion force, slows the magnet speed through the tube. Okay. Question number 9. Another good question. Be careful. An electromagnet is placed next to a coil. What do you mean by electromagnet? If you remember in a previous lesson, we studied what is the electromagnet. Electromagnet, it means that the magnetic field produced by the current. Okay. To, like, for example, we need a current and we need a supply to produce a magnet from the electricity, from the current. In chapter 5, section 2, we studied when the current passes through the coil and solenoid or a straight wire, this current can produces the magnetic field. Okay, electromagnet is placed next to a coil of wire. We have electromagnet. Guys, look. We have electromagnet, a coil of wire, and also we need a battery. Okay, we need a source of electricity like a battery, positive and negative. Okay, so the direction of the current is the direction of the conventional current in positive direction. Guys, be careful. This is what? This is DC battery. What is this? This is DC battery that produces the current. Okay, and the current in the DC battery is always moves from the positive side. Okay, not from the negative side, from the positive side, and the current goes up here and it goes down. So the current moves from left to the right according the type of the battery that connected like this. The direction of the current is always in the direction of the positive side, okay? And also we have a coil located next to the electromagnet. We have a coil. A coil of wire which is connected with the resistor. We have resistor here. Okay, guys, look. Now we know that the direction of the current by the battery, always the direction of the current in the battery. Like, for example, in all DC battery, we have positive and negative. The direction of the current is always the same direction of the positive side, okay? And now we know that the direction of the current in the battery, so we can say that the direction of the magnetic field also can be determined by the current. According to the right-hand rule, the direction of the current is down. Here is down, okay? Where is my thumb? My thumb is here. So this end becomes north and this end becomes south. So without this in the question, the magnetic field was mentioned here, okay? The magnetic field mentioned here. But without the mention of the magnetic field, the student must know the direction of the magnetic field here by knowing the direction of the current. If you know the direction of the current, you can determine the direction of the magnetic field. Now we know that this current produces the magnetic field into this coil, and this end is north and this end is south pole. This is electromagnet. What is this? This is electromagnet. Okay, so we can produce the magnetic field by the electricity and by the current. According to the Lenz's law, what will be the direction of the induced current in the resistor in the following cases? And also we have a switch here. Guys, be careful. We have what? We have switch here. Okay, if you open the switch, guys, look. Open the switch. Open switch. What happened? By opening the switch, what happened to the current? Absolutely, current decreases. If you open the switch, there is no movement and there is no flow of charge. What happens to the current? Current decreases. When current decreases, what happened to the magnetic field? Magnetic field also decreases. When magnetic field decreases, it acts as such as moves away. It means that what? Moves away. Can we treat with the open switch? Open switch as moving away a bar magnet. Okay. So how about for closing switch? If you close the switch, when the switch is closed, what happened to the current? Current suddenly increases. When the current increases, what happened to the magnetic field? Also increases. Increasing magnetic field acts as approaching or moves away. Absolutely approaching. When the magnetic field increases, it means that the magnetic field approaches to the coil. Okay, it acts as approaches. Okay, so in both cases, guys, magnetic field is directly proportional in the solenoid with the current. When current gets more, what happened to the magnetic field? Magnetic field also gets more. The relation between magnetic field and induced current, and the current in the source by a battery is directly proportional. So we have to find the direction of the current in the resistor in the following cases. Case number 1A, the magnetic field suddenly decreases. When does magnetic field decreases? In this case, guys, look. In this case, what happened to the magnetic field? Magnetic field decreases. Look. When magnetic field decreases, it means that current decreases. When does current decrease? The switch must be open. The magnetic field suddenly decreases. When does the magnetic field decreases? After the switch is opened. After the switch is what? Is open. Okay. When the switch is opened, the electromagnet acts as a moves away. Okay. So it means that the electromagnet moves away. When the electromagnet moves away, the north pole moves away from the coil. this end becomes what? South pole according to Lenz's law. And the other end becomes what? North pole. If you have South pole and North pole, we can determine the direction of the current very easily by using right hand rule. Your thumb in the direction of the north, and here the 4 fingers is down. The 4 fingers is what here? Is down. So the direction of the current in the resistor directed from what? From left to right. From what? From where? From left to right. Look at the answer. From left to the right. So when does the direction of the current directed will be from the left to the right? When the magnetic field suddenly decreases after the switch is open. If the question is changed in the Wizari exam, guys, listen carefully. If the question says the magnetic field suddenly increases after switch is closed, increases after switch is closed, it means that the electromagnet approach or moves away. Absolutely approach. If you approach the north pole of the end of this coil, this end becomes what? This end also becomes north pole, opposes each other. And the direction of the current reversed from right to the left. Okay? Branch B, guys. In branch B, the coil is moved closer to the electromagnet. The coil is closer to the bar magnet. Okay? The coil close to the electromagnet. If you close the coil into the bar magnet, by this end is north, and this end becomes what? The same pole. Okay? And the other end becomes south pole. By approaching the north, closing the coil into the electromagnet, this end becomes the same pole of the approaching. Okay? And the direction of the current for branch B, guys, for branch B, the direction of the current will be from right to left. From right to left. So this is question 9 in chapter review, one of the very nice and very good question. Okay, so the conceptual challenge has skipped by Ministry of Education. Okay. Now Faraday's law of induction predicts the magnitude of the induced EMF and the current. Okay, guys, listen to me. But Lenz was the first scientist discover and determine the direction of the induced current. But Faraday, he found the magnitude of the induced current and induced EMF. How can we determine the magnitude of induced EMF? By using this relation according to Faraday's law. Electromotive force EMF is equal to negative N change flux over time. For single loop, for what? For single loop, the equation of Faraday's law becomes what? Flux over what? Over time. Okay? When does EMF is equal to negative flux over time? If the coil is single and the number of turn is equal to 1. Lenz's law allows you to determine the direction of the induced current in a circuit. Lenz's law does not provide information on the magnitude of the induced current or the induced EMF. To calculate the magnitude of the induced EMF, you must use Faraday's law. By Faraday's law, we can determine the magnitude of the induced EMF and induced current. To calculate the magnitude of induced EMF, you must use Faraday's law of the magnetic induction. For a single loop of a circuit, this may express as follows. EMF is equal to negative flux over time. According to Faraday's law, the magnitude of induced EMF directly proportional. The magnitude of the induced EMF directly proportional to what? To the time rate of changing magnetic flux. What is the relation between the time rate of changing magnetic flux with the electromotive force? Is directly proportional. When both delta flux period of time increases, what happened to the electromotive force? Increases. What happened to the induced current at constant resistance? Increases. Okay? To the change of the magnetic flux passed through the coil. This is the main equation of Faraday's law. Guys, look. EMF is equal to negative. What does negative sign indicate in the front of this number of turn in the Faraday's equation? The negative sign indicates the Lenz's law. When the magnetic field increases, delta B becomes positive. And when the delta B is positive, the EMF and the induced current becomes negative. Okay, according to Lenz's law. The negative sign indicates that the induced magnetic field that created by the induced current is opposes the change of the external magnetic field. Okay, the negative N change flux over time. If you remember, flux is equal to what? AB cosine theta. Okay, now we have two equations, guys. Equation number one, by changing, so you can replace this magnetic field, this magnetic flux into the equation of Faraday equation. Delta what? And instead of flux, write down what? A, B cosine theta. Okay, over what? Over time. Okay, now this change, first time for A and the second time for B. We have change in area and change in magnetic field. For the first equation, like by changing area, changing area. What do you mean by changing area? Delta A. Delta A is equal to what, guys? Delta A is equal to A2 minus A1. So you can replace, so you can give this delta for the first time for the A, for the area. EMF becomes what? Negative N, bring down B cosine theta, B cosine theta. What is remain? Delta only for A. Delta A over what? Over delta T. This is equation number one. This equation can be used to determine electromotive force and induced current, because EMF is equal to I, R, and I is equal to what? I is equal to EMF over R. After find the EMF, you can find the amount of the induced current. Okay, guys, this equation can be used when the area is changed of the coil. When the area of the coil and solenoid is changed, you have to use this relation. Okay, this is equation number one. Equation number two, by changing magnetic field. When magnetic field changes by approaching and moves away the bar magnet into the coil, or by increasing and decreasing the strength of the magnetic field of electromagnet, by changing magnetic field like delta B. For the second equation, you have to give this delta for what? For magnetic field. Delta B is equal to what? Is equal to B2 minus B1. Replace into this equation, guys. EMF is equal to what? Negative, bring down A and cosine theta. And A cosine theta. What is remain? Delta B over delta D. Now, so after finding EMF, you can determine the induced current, EMF over R. Guys, how many equations do we have of Faraday's equation? We have two equations. The first, so both equations are based from the main equation of Faraday's law. What is this? This is main equation of Faraday's law. Okay. We have two equations. The first equation, EMF is equal to negative NB cosine theta delta I over delta T. This equation can be used to determine the electromotive force when the area of the coil is changed. Okay, when the area of the coil is changed, so we have to use this relation by changing area. It should be mentioned in the question. The second equation can be used when the magnetic field is changed. Okay. EMF, induced electromotive force, measured in volt, and number of turn of the loop. B, the strength of the magnetic field, change flux, measured in Weber, area, and B cosine is the component of the magnetic field that is perpendicular to the plane of the loop. The angle between magnetic field and the normal to the plane of the loop, and to the area, the normal to the plane of the loop, it means that the area vector. Okay, T is the time. And A cosine delta B over delta T, delta B, B final minus B initial, B2 minus B1 is the same thing, okay? The second equation when the area is changed. What are the variables that can give rise to this, the EMF? By changing applied magnetic field, changing field, by changing area, or the orientation of the coil, we can get the change in magnetic flux. What is the use of the Faraday's and the application, the function of the Faraday's law? To find and determine the magnitude and to calculate the induced EMF and induced current. In Faraday's law, what does the negative sign indicate? To the negative sign indicates the Lenz's law. Okay, induced magnetic field indicates that the induced magnetic field opposes the change in the applied magnetic field as stated by the Lenz's law. What does average time rate of the changing magnetic flux depend on? Depend on the area, the angle, the area of the coil magnetic field, and the orientation of the coil into the magnetic field. Question 3 in chapter review, guys, look. What 4 factors affect the magnitude of induced EMF in a coil of wire? Induced EMF in a coil of wire. The factor that affects the induced EMF in a coil of wire. EMF is equal to negative N delta A B cosine theta over time. The 4 factors that affect the magnitude of the induced EMF according to this relation, it depends on what? The factors that affect the induced EMF magnetic field component perpendicular to the plane of the loop, B cosine theta, okay? And the area of the coil, B cosine theta, the area of the coil, number of turns, and the time in which changes occur, okay? Area of the coil, time in which changes occur, and the number of turns of the wire in the coil. Guys, we have some notes to solve the questions that related with the Faraday's equation. For the ring and the single loop, number of turns is equal to 1. When the plane of the loop, be careful, guys. When plane of the loop and the area of the loop, the coil of the loop, is placed perpendicular to the magnetic field, theta becomes 0. When does angle become 0? If the plane of the loop is perpendicular. When does plane of the loop becomes perpendicular? When the area vector is parallel to the direction of the magnetic field. Okay? Which means that the area vector becomes parallel to the magnetic field. When the plane of the loop or coil is parallel to the magnetic field, angle is 90 and there is no magnetic flux, there will be no induced EMF and there will be no induced current. If the radius of the ring is given instead of area, if the radius of the ring is given, so you have to convert this radius into the area. How? By using this relation, pi r squared. But you have to make sure that the radius is given in meter, not in centimeter. Okay? If the radius is given in centimeter, you have to convert to meter, divide by 100. Sometimes the coil, it doesn't necessary, guys. The coil, circle, rectangle, square, okay, it depends on the question. It doesn't matter. The coil is circle, rectangle, and square. If the coil is circle, or when the radius is given, it means that this coil is circle. So you can determine the magnitude of the area. But instead of radius, if the length, if the coil shape is rectangle, and instead radius we have length and width, how can we determine area? Length times width, okay? The area of rectangular coil shape is length times width. If the resistance is given to find the current, you have to use this relation. EMF is equal to, the induced current is equal to EMF over resistance. The SI unit of Tesla per second is if the SI unit Tesla per second is given, it means that there is a change in magnetic field period of time. For example, if you see 5 Tesla per second, what do you mean by this 5? This 5 should be delta B over delta T. How did you know this is delta B over delta T? By units. If you see any number, after the number, if you see Tesla per second, it means that this is change in magnetic field. So how about if you see like 3 meters square per second? What do you mean by this? It means that this is change in area over time. And maybe positive and maybe negative. It depends on the question. Positive in the case of increasing, negative in the case of decreasing. Okay? If in the case of increasing the time rate of the change magnetic field, when the change in magnetic field increases, delta B over delta T becomes positive when it increases. So, and EMF becomes what? Negative. EMF, sorry, EMF negative, current negative. For delta A is the same thing. If delta A over delta B is positive, increases, so EMF still positive, current negative. The amount of the current also, sorry, both negative, not positive, sorry. The EMF becomes negative and current, induced current also negative. In the case of increasing, okay? How about decreasing? Guys, look. In the case of decreasing, look. If delta B over delta T is negative, when does delta B over delta T becomes negative? In the case of decrease or increase? Absolutely decrease. Decreases. EMF becomes what? Positive. Lenz's law. Induced current becomes what? Positive. But if delta A over delta T is negative, also decreases, and EMF and current still positive, okay? EMF is positive, the amount of the current still positive, okay? Note number 10, if the ring or coil is pulled steadily out, it means that the magnetic field decreases, okay? Until reaches zero. Pull steadily out, after pull steadily out the bar magnet, the final magnetic field becomes zero. Guys, if you see in the question, the coil pulls steadily out, or the coil is removed, or the coil exits in the field, then final magnetic field becomes what? Becomes zero. When does B final become a zero? When the coil pulls steadily out, or when the coil is removed, or when the coil exits in the field. If the ring places into the magnetic field, B initial becomes zero, like dropping the magnetic field, like drop, okay, or dropping the magnetic field, B initial becomes zero. If delta B over delta T, delta A over delta T increases, EMF negative, current negative. If delta B over delta T, A over T decreases, EMF positive, current still positive, okay? The minus sign in the front of the Faraday's equation indicates the Lenz's law. The negative sign indicates that the induced magnetic field opposes the change in the applied magnetic field, as stated by the Lenz's law. Question 4, if you have a fixed magnetic field, what do you mean by fixed magnetic field, guys? Fixed magnetic field, it means that B is constant. We cannot change B, is constant. And we have a length of wire. We have what? Length of wire. How can you increase? Increase what? Induced EMF. How can you increase EMF across the ends of the wire? According to Faraday's law, A, B, cosine theta over time. According to Faraday's law, so you have to wrap and wound the wire into a coil that has many turns. Why? Because EMF is directly proportional to the number of turns. More turn provides more EMF and more induced current. Wrap the wire into a coil that has many turns, move it in and out of the magnetic field quickly. It means that in a short time, okay, short time produces more EMF. Why? Because EMF is inversely proportional to the time at constant magnetic field and area. Okay, guys, that's all for today. Inshallah, in the next lesson, we are continuing to explain and solve the other. We will solve the other questions that related with the Faraday's law, and we have many questions, many good questions that all years they will be given in the Wizari exam. So if you have, if you are struggling with any question, feel free to leave in the comments, and inshallah I will answer as soon as possible. Thank you for listening, and I hope you benefited from my lesson.